Okay, now next we continue our discussion of symmetries with exercise 16. So here we are given an infinitely long strip of equally spaced capital H's. We have to describe the symmetries of this strip, and we have to also determine whether the group of symmetries is abelian or not. So like we saw in the last video, this is our a finite portion of that infinitely long strip of equally spaced H's. So you can see that the symmetries that this strip can have, they include the symmetries of a rectangle, because a single H is a rectangle, and we already know, and in fact it's a non-square rectangle. If you look closely, you will see that every H is a non-square rectangle. Now the symmetries of a rectangle we have already seen. There are four symmetries. One of them is identity, and then we have the counterclockwise rotation through an angle 180 degree, where the center of rotation is this middle point. So you have like this, okay, and then you have a reflection about a vertical axis that passes through that central point. So you can flip the entire strip like this, and you get this symmetry. And you of course have also the reflection about a horizontal axis passing through this central point, so you get this. Note one more thing, that while we were performing these symmetries, the entire strip actually came back to a similar looking position. That's why those individual symmetries of a rectangle are also symmetries of this strip, but because of the presence of other H's, we will have some additional symmetries, and those additional symmetries are translations. Consider this fingertip of the thumb tip as, say, the origin. Now by translation we mean translating along the length of the strip by a unit distance, where a unit distance is a distance from one edge to its adjacent edge. So I can translate like this to the right, or I can translate like this to the left. And also not just by one unit, I can translate by any say 2 units, 3 units, or any integer units, either in this direction or in that direction. So we can write the symmetries like this. So these are the translations. Of course I am not going to write all these things, you can understand. You can write the actual full elaborate solution on your own. So Tn denotes the translation along the, where the axis of translation or the line along which you are translating is actually along the strip, parallel to the strip, and n is any integer absolute value of n determines the unit by which you have to translate, whether it is 1 unit translation or 2 units translation, that thing. And the sign of n will determine you have to translate to the right or to the left. If it is positive, then we translate towards the right, otherwise towards the left. So these are the translations. And along with that, we of course have our familiar symmetries that have come from a rectangle. For that, what we do, we consider R180. Note one thing, that if you take n equal to 0, then that is translation by 0 units, that means doing nothing. So the identity symmetry is included in this list of translations, which is T0 or T0. So we don't have to mention that separately. Now we concentrate on the symmetries that are coming from a rectangle. So there we have R180. Now what does R180 mean in this situation? In this situation, it means that of course again we are going to rotate the figure counterclockwise through an angle 180 degree. But what will the center of rotation be? The center of rotation will be the central point of that edge which is at the same position as the origin thumb. Okay, so it is like this. And then we have a vertical reflection. Vertical reflection means a reflection about an axis that is vertical and passing through that central line. But which axis? That also is the axis that passes through the origin thumb. Okay, so it's like this. Okay, so that is also a symmetry that brings all the H's back to their, not to their positions, but ultimately the figure looks the same. And there is that horizontal reflection, which of course for this one we don't have to look at the central, origin thumb. It's reflection about this axis that passes through this connecting line of each edge. So it's like this. Okay, so that is the edge. But these are not the only symmetries, because someone, for example, may want to rotate not about this point, not taking this as the center of rotation, but say this as the center of rotation. What does it do in that situation? So that's why we have to take, in fact we also have to anyway consider all the possible combinations of these things. These are symmetries, so their combinations also are going to be symmetries. Now if you take combinations of R180, V and H, taking any two at a time, then we already know from our discussion on symmetries of a rectangle that they again produce one of these things, one of these three things, or the identity. So there is no point taking compositions of this, but we have to take compositions of Tn with these things. Also, if you note one more thing, that if you take two Tn's, say Tn and Tn, then that means you are performing two translations. Whatever the values of n and m may be, you can see, you can convince yourself that such a composition again is going to be another Tk, suppose. For example, if it is T1 and T2, then you perform say T1 first and then T2. That is equivalent to performing T3 once. Like that, you can formulate the rules for composing two translations, and you can see that ultimately the result is again a translation. But these are something new. Tn R180 and also R180 Tn, because we have to consider all possible compositions where n is an integer. Okay, then Tnv and Vtn where n is an integer, and finally Tnh and Htn where n is any integer. Note one thing that is different in this case from the symmetric groups we have seen so far. Here, because there are infinitely many translations, so the group of symmetries in this case is infinite. The groups we have seen so far, all of them are finite, but this one is infinite. And these are all the symmetries. You won't get anything else. You can pretty much convince yourself looking at this picture, thinking about it and flipping the thing you can make such a strip by drawing H's, and you can play with it, and you will soon realize that these are the only symmetries. Now the second part of the exercise asks us whether this group is abelian. This group is not abelian. Note that okay, let us see why it is not abelian. We are going to calculate T1R180 to show that it's not abelian. It's enough to show that two specific symmetries do not commute, TR180 and R180T. T1. Okay, so according to our rule for this composition, we are going to, since we are treating this as a function where the input will be put here, so we are going to apply first R180 and then on that result we are going to apply T1. So let us hold the strip correctly. So this is the initial position of the strip. So I am going to now perform R180 first, and then on that I am going to perform T1. So R180 is, see, this origin thumb is here, this is fixed. Okay, so R180 is this, and then keeping the position of the origin thumb, I have to translate towards right by 1 unit, that is T1. So this is the final position of the strip after performing this composition operation. Note that this particular edge, whose sort of, you can say its vertices we have labeled as A, B, C, D, they lie to the right of this origin thumb from this perspective. Okay, now let us go back to the original position of the strip, and now let us calculate R180 T1. Now we are going to perform T1 first and then R180. So if we perform T1 first, that means we come to this position. Now the origin thumb is here, and now I am going to perform a 180-degree rotation counterclockwise, but now about this point. This is the center of rotation, because according to the rule we have, according to what we have agreed on, the rotation has to be about a point where the origin thumb is lying. So that means I rotate like this, and the origin thumb is here. This is again a symmetry, but note that the labeled H has now come to the left. So actually these two compositions take points to different places. Okay, so that's why they are not equal. So they are not equal. Hence, the group of symmetries of the strip is not abelian. So we have got an infinite non-abelian group of symmetries. Okay, then this one, snowflakes. For each of the snowflakes in the figure, find the symmetric group. And locate the axis of reflexive symmetry. But where are the figures? The figures are here. Okay, they may not match with what is given in the text, but I have tried to make them as close to the text figures as possible. Okay, so these are some figures of snowflakes, and there is one on this side also. We have to find the symmetry group. You can see that each one of them has a hexagonal symmetry. Hexagonal symmetry means if you join these vertices, you will see that roughly you will get a regular hexagon in each one of them, and that's why each one of them will have the symmetry group that is the same as the symmetry group of a regular hexagon. And that's why, and we already know, we have found the symmetry group of a regular n-sided polygon, which is the dihedral group Dn. So in this case, for each one of them, the group of symmetries is D6. In each of the, or not in, for each of the snowflakes its group of symmetry is D6. They are also asking us to find the axis of reflective symmetry. The axis of reflective symmetry you can find by going to that exercise where we have been asked to describe all the symmetries of Bn. There in the solution we saw this. If n is even, then half of the axis of reflective symmetry are obtained by joining opposite vertices. For example, this one, this is an axis of reflective symmetry. If you reflect like this, then you can again have a similar figure. So 1, 2, 3, so 3 axes of symmetries are obtained like this, and half of the axes of reflective symmetry are obtained by joining midpoints of opposite sides. So you have these axes also, this one, and this one. So there will be 6 axes of reflective symmetry in total, and in fact for all of them it's the same thing, no matter how intricate the ultimate structure of the snowflake is. As far as symmetry is concerned, it's D6. Okay, and those are the axes of symmetry. So if you want, you can write here that half of them are obtained by joining opposite vertices and half of them are obtained by joining midpoints of opposite sides, but I am ending it here itself. And then something dangerous from biology, virology actually. determine the symmetric group of the outer shell of the cross section of the human immunodeficiency virus HIV. Shown below. Shown below means this is the figure which it looking at it, I cannot help but think that this looks somewhat like coronavirus. Anyway, so this is the cross section of the outer shell of an HIV. Now we have been asked to find the symmetry group of this picture. What it represents, that does not matter now. It's for us, it's a geometric figure for which we have to find the symmetry group. Now looking at this extremely symmetric outer part, okay. I have an immediate confusion. We have been asked to determine the symmetry group of the outer shell of the cross section. Okay, that means we have to consider only this part. I think we should not consider the part that lies in the middle, including this. Maybe these are DNA strands. I don't really know. Say determine the symmetry group of the outer shell of the cross section of the human immunity. Okay. So previously I was thinking that we have to find the symmetry group of the entire cross section, but only the outer shell. Then we have to calculate how many these protrusions are there. Let me just calculate, or let us just see. 1 2 3 4 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28. Okay, so this will definitely have the symmetry of D28. Because as far as symmetry is concerned, the outer shell, it looks almost like a 28-sided regular polygon. So that's why D28. However, note that if you look at the cross section, the entire cross section, then that has the only symmetry of that cross section is the identity. Why? Because now you cannot rotate. If you rotate, this central part will not look the same. Okay, only if you rotate through an angle of 360 degree, a complete rotation, then only the things come back. Also, you cannot make reflections if the central part is considered. The orientation of these two strands of whatever material they are, that will change, because it's not symmetric. You can see this will come to that side and it will be like this if you reflect through an axis that is perpendicular to this cross section in this sense. So okay, so outer shell means, I hope that by outer shell they mean this part. Okay, if that is the case, then it is D28. Then we come to exercise 19. Does a fan blade have a cyclic symmetric group or a dihedral symmetry group? A fan blade is manufactured in such a way that it will throw air in only one direction, right? So that means if you reflect the fan blade, the orientation actually will change. I mean, the blades are not like this. If a surface like this rotates, then it will not move air. It has to be bent at an angle, then only it will move air in one direction. Any fan blade, any propeller, helicopter blades, things like that. So that's why if you flip, then the orientation changes and you don't have that same effect. So that means in the symmetric group of a fan blade, we cannot have reflections. So that's why the symmetric group has to be cyclic. Okay, these are rather somewhat easy. Bottle caps that are pried off. Okay. Typically have 22 ridges around the ring. Around the ring, find the symmetric group of such a cap. find the symmetry group of such a cap. Okay. Now a bottle cap, of course, it has orientation in the sense that one face is facing the bottle, which is which is towards the bottle, and the other face is facing you. So what I am thinking is that since we have been asked to find the symmetry group of the bottle cap itself, then if that orientation is taken into account, then clearly if you flip, if you reflect, then the orientation will change and you will not actually get the cap in that similar looking position, because if it's like this, where on that side the bottle is there, that is as if you are looking from the top of the bottle, then the cap is in one orientation. Now if you flip, you change the orientation, so now you are looking at the face that was facing the bottle previously. If that's what they mean, then just like the fan blade case, in this case also no reflection is allowed. So because of the 22 ridges around the rim of the cap, the symmetry group will be the cyclic group with 22 elements. Reflections are not considered, but if there is a way of considering reflections where they are also symmetries of the bottle cap, then it will be the dihedral group D22, because their reflections are also allowed. But since the entire bottle cap has been considered, so I am assuming that it's the case where the orientation will matter, and in fact the two sides are not the same. No. One side is closing the bottle, actually you have the ridges on that side, you can understand what I am trying to say, and the other side is open in the sense that how can I put it? If you put the bottle cap in water and the side that is facing the bottle originally, if it is now like this, if it is facing up, then that is like one side and the other side is not like that. So that's why the orientations are different. If you flip the bottle cap, then someone will know that it has been flipped. That's why the symmetry group in this case, let me just simply write C22, the cyclic group of order 22, or the cyclic group having 22 elements. It will have 22 rotations, identity included. Okay, then what group theoretic property do uppercase letters, okay, now we come to letters from the English alphabet. Uppercase letters F, G, J, L, P, Q and R have, that is not shared by the remaining, have that is not shared by the remaining uppercase letters. If you look at these letters, you will see that look at these letters means look at the geometric figure that is the letter. You will see that the only symmetry each one of them has is the identity. If you rotate or flip, rotate through a non-trivial angle. Non-trivial angle means don't rotate it through an angle 360 degree. That is equivalent to the identity. If you rotate through any other angle that is not a multiple of 360, then the figure will not look the same for each one of these things. Also, there is clearly no axis about which you can reflect the figure and have the same looking situation. Have the figure looking exactly like how it was looking before the operation was performed. So that's why in each one of them the only symmetry is the identity. For any other figure, say you take A clearly has an axis of reflection that is vertical and passes through this tip of A. If you reflect A about that axis, then it will look the same. For B, this horizontal axis is an axis of reflection. For C also like that, you can consider the horizontal axis. For D, you can consider the horizontal axis. For E, you can consider the horizontal axis. The fact that F does not have one horizontal bar like E has makes it lose that symmetry. Okay, so here I think I need some ink before I write. For each of these letters, the only symmetry is the identity. Then like that, another one, exercise 22. What symmetry property What symmetry property does the word zoonosis? Okay, never heard of it. Symmetry property have when written in uppercase letters. It means a disease of humans acquired from animals. That's what zoonosis means. Okay, so if we write the letters like this, what are the symmetries that this can have? If you reflect about any axis that is vertical and lies in any position, say symmetric with respect to one particular letter, then that does not give us a symmetry of the entire word, because S will come here and also S will look like this. I mean, or if you are not viewing it as a reflection, you can go to that side and look at the word from there, from that side. That will make it make this S look like this, and the S has changed position also. I mean, now it's towards the right end, there it will be towards the left end. So no vertical axis of symmetry. Any horizontal axis of symmetry? If we flip this figure, then S gets flipped. If S gets flipped, yes, then it becomes again that S is creating a problem. So no horizontal axis of symmetry also. Any rotational symmetry, if we rotate, say for example with the middle point of N, you know what I am calling the middle point here, as the center of rotation. Through a 90-degree rotation, of course, will make it perpendicular. That's not an option at all. If we rotate it through 180 degree, then so this is why I should have made one cutout for this. N becomes Z, and then again, okay. That means if I rotate it like this through 90 degree, then I come to this position, and then again if I rotate, then yes, N does look like N again, but S also looks like S, S looks like S, and Z or C, whatever you want to call it, it looks like a bed. If I make a 90 degree, a broken bed, a 90 degree rotation, and then if I rotate once more, then it looks like that. But the thing is that their positions will change. No? That means if I make this rotation, then it will be like this. that's not the same as this one. So in spite of having all the letters still making sense and representing actually the same letters, but the word has changed, so it's not a symmetry. So the only symmetry for this word is the identity. That's what I am concluding. I hope my analysis and observation they are correct. Anyway, if you spot any mistake, then you can always write in the comment section. The only symmetry of the word written in uppercase letters is the identity. Still, there is one more exercise of this type. Exercise 23. What symmetry property do the words sees and swims have when written in uppercase letters? The snowflakes have fallen down and they have settled on the ground. Okay, let them stay there. Okay, here, well, if you write more in uppercase letters like this, M and W are actually not, I mean, you will not get one from the other if you reflect the figure by about a horizontal axis, because the W looks a little like this, whereas the vertical M has vertical bars. Here for W it's not, these bars are not vertical, but you can understand what the author is trying to say. And in fact the answer is given at the end of the book, and it has been written that all of them has rotational symmetry through an angle 180 degree. Cis, however, of course, is, if you rotate this through an angle 180 degree, it will still remain cis. And so is the case with swims. But here again, that M and W, W has to be written like this, so that when you rotate it, it looks like M. So you can write, you can agree with the author here, but actually that's not what will happen. The words have words means all of them. Rotational symmetry written in uppercase letters, that is understood. And finally, this is the last exercise. For each design below, determine the symmetry group. And also ignore imperfections. Okay, ignore imperfections. In the text itself, the figures are a little imperfect because they are actual photographs. Well, these are not actual photographs. The snowflakes were actual photographs, but these have been drawn. In the text itself, somewhat the author feels they are imperfect, but the drawings I have made, they are naturally even more imperfect. So here you have to ignore imperfections even more. Okay, so these are the figures that have been given in the text. So for them you have, I hope you can see, for them you have to find the symmetry group. So let's look at them one by one. If you look at this figure carefully, you can see a 2, and that 2 has been written in a cyclic manner like this. Okay, these 2's are there. Now note that you can almost immediately see that this arrangement has the symmetries of a square. Here, because of my imperfection, the 2's don't look alike. Also, there is an outer layer, there is a layer that is covering these 2. Okay, the head of all the 2's. So that those layers are not symmetric, but you can understand that they are supposed to be symmetric. They are supposed to be alike. Now, because of that, one will come to the conclusion that the symmetric group of this object, this figure, is the same as the symmetric group of a square, but that is actually not true. Of course, it has symmetries. It has the rotational symmetries of a square. If you rotate with this as the center of rotation through an angle 90 degree, then the figure becomes like this, which again is just like the previous one, or by 180 degree, or by 270 degree, or by, if you rotate by 360 degree, you come back to the same position. So the rotational symmetries are there. Okay, but what about the reflectional symmetries? If you reflect this about any axis, about which you feel a square has which is also an axis of reflectional symmetry for a square, then the thing will be different. You see, if you reflect this, I don't know if you can see, the 2 has now changed. It's not 2 anymore. So if you reflect, then that is not a symmetry. So there is in fact no chance of having any reflection. So that's why, unlike the symmetric group of a square, which is the dihedral group D4, this figure has only rotational symmetry, 4 rotations. That's why it's the cyclic group C4. Okay, because of this one-sidedness of the individual parts of the figure, reflections will not give us symmetry. For the second figure, it's a pentagon, and inside there is a star with 5 it's like a starfish with 5 hands or 5 limbs. That one-sidedness is now not present here. This will have all the symmetries of a regular pentagon. That means here the symmetric group will be D5. Just like that, the one-sidedness is not available here. Here if you count, it looks like 1, 2, if you count only the skinny wise, not the fat wise, okay. If you count the skinny wise, then let's count from here, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 skinny wise. Now unlike this case, here you can have reflections. So here the symmetry group is the dihedral group D8. Then what about this figure? Actually this figure I wasn't able to draw properly. These parts are supposed to come till this, like that. These also have to be extended. But you can see in the text the proper figure is given. For this one, you can have rotation through an angle 180 degree. 90 degree of course will not work, but if you rotate, you see, you look at the figure carefully. Here this has come down, the uppermost bar. Here the lowermost bar is going up. 90 degree, 180 degree. Again, it's like an S, but with 2 parts. S, S. So identity is always a symmetry for every figure, no matter how asymmetric it is. And then a 180 degree rotation. Does it have any reflection? If you reflect about this axis, say, then it does not remain S. See, it becomes like this now, not like this. So that's why no chance of reflection. Similarly, if you reflect about a vertical axis, then also it is no longer an S-like structure. So here the symmetric group, since here also there is a one-sidedness, wherever you will have one-sidedness, there the group, no reflection will be there and the group will be cyclic. So here the cyclic group has only 2 elements, 2 rotations. One identity, rotation through an angle 0 degree, and the other is rotation through an angle 180 degree. Here there is no one-sidedness, and here you can see that the symmetries are the same as the symmetries of a square, because ultimately this is inside a square. So it will have all the symmetries of a square, but it does not have any more symmetry. I mean, you can convince yourself that it does not have any more symmetry. It has all the rotational symmetries, a rotation through an angle 90, 180, 270, 360. Okay. It has all the reflectional symmetries. you can reflect about this axis or about this axis or about the two diagonals, you will get back the same thing. That means here the symmetric group is the dihedral group D4, and this one I could not do justice at all. It's looking extremely awful. You look at the text and you will see the difference, but roughly you can understand what the figure is. And this figure has a one-sidedness. You see, there is a, I mean, if you are looking at these things and you are thinking of them as claws, then the claws are rotating in a clockwise direction. So that gives this an orientation or one-sidedness. If you reflect about any axis, then that sense of rotation changes to counterclockwise. So that's why this figure also does not have a reflectional symmetry axis of reflectional symmetry. However, if you look at the actual picture in the text, you will see that it does have rotational symmetries, because it can be made to sit inside an equilateral triangle. So it has 3 rotations. So that's why here the symmetric group is the cyclic group C3. Then there are others also. This one I recognize. This is a symbol which represents biohazard. Here also, because of lack of one-sidedness and because of the fact that it can be made to sit inside an equilateral triangle, here note that in the previous one there was one-sidedness, so the symmetric group was C3, the cyclic group C3. Here there is no one-sidedness, so the symmetric group is the dihedral group D3. In this case, there are 16 of these spikes and there is no one-sidedness. So it will have the same symmetric group as a 16-sided regular polygon. So here the symmetric group is D16. In this case, this also has been awfully drawn, but if you see, it represents a 7-sided regular whatever it is. I mean, it matches with a 7-sided regular polygon, a heptagon. 1, 2, 3, 4, 5, 6, 7. So here D7, there is no one-sidedness. Just like that, here also there is no one-sidedness. Although you can see that there are, say, 1, 2, 3, 4, 5, 6, 7 things, or am I missing one? 1, 2, 3, 4, 5, 6, 7, 8. But 4 of them are big and 4 of them are small. 4 of them are not coming all the way to this level. So it has the symmetry group of a square. And that's why D4. For this one, D5, because pentagon. There is no one-sidedness, and this also has been very badly drawn. I mean, these things should have been drawn uniformly, but I was not able to do that. Plus, towards the end, I was rushing through the thing to complete these figures. That took a hell lot of time to draw. You can see that there is a one-sidedness. The lines here in one triangular part, the lines are going like this, and here also the lines are going like this. That means if you look at the figure like this, then among these two sides of the triangle, one side is receiving all the lines, or in other words, saying more geometrically, more rigorously, these lines are parallel to the right edge, the edge that lies on the right hand side. Here also the lines are parallel to the edge lying on the right hand side. Because of this handedness, and because there are, you can count, you go to the actual figure, you can count that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 such triangles are, am I counting it correctly? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So that's why, because of that one-sidedness, there no reflectional symmetry can be there. So here the symmetry group is the cyclic group C10, having 10 rotations. So with this, you can write these things elaborately. You have understood the concept here now. So with this set of exercises ends. In the next video we will go to abstract group theory in the next, that is whatever we have next. So with this I end this video. If you are new here, please consider subscribing if you find these things useful. So that will be all for today. Signing off, this is me, Lucifer, from a mathematical room. Have a nice night.